YouTube, there's a couple of more exotic rational functions that we're going to graph in this video, but we're going to do them really quickly here. So let's go ahead and start by taking a look at how we would graph this rational function h of x given by 3x over x squared plus x minus 2. Now, the first thing I want to mention is this: you always simplify first, and by simplify what I mean is this: factor the top and the bottom if possible. And I've actually provided an example of something that factors on purpose in the basement here. We say x minus 2, x plus 1 would be the factors of this basement polynomial here, but I noticed that nothing cancels out on the top and the bottom. Like if I had an x minus 2 on top, these would cancel out. But in this instance, we don't have anything that cancels, which is fine. That just means we can start doing our job. But in terms of graphing this, what we want to do is we always start by finding some intercepts on your graph when you graph something. So start with your y-intercept. Now your y-intercept, we know, is what we obtain when we plug in 0 for x. So I mean, we can show our work over here, but another good reason why we factor everything is because it's easy to plug in 0 for factors and see what you get. So for instance, on the top I'm going to get 3 times 0, which is 0. And in the basement I would get this 0 minus 2, which would be negative 2. And if I plugged in a 0 here, I'd get 0 plus 1 is 1 essentially. And so I get 0 over negative 2. Now the important thing is that I can plug those things in, but I get 0 in this instance. So we say 0, 0 would be on our graph. So that's a y-intercept. As a matter of fact, that's an x-intercept also. So when we start now searching for x-intercepts, we say to find x-intercepts, of course, you always plug in 0 for y and solve for x. Now, we have not a y value, but an h of x value. And if we were to plug in 0 for this whole thing and say, okay, what causes this fraction to be 0? That is, maybe I'll write it off over here on the right. But if I were to set this whole thing equal to 0, the only thing that's ever going to cause a fraction to be 0 is if the numerator is equal to 0. So essentially, to find this, all we have to do is set the top equal to 0 and solve it. So we say, well, what if 3x were 0? What would x be? We would get x equals 0. Okay, so we'd say, well, then this must be my x-intercept, which basically verifies what we just confirmed with our y-intercept. Okay, now moving on, we say the next thing on our list is always to find our vertical asymptotes, which, by the way, only occur where this rational function would be undefined. So where would this be undefined? We say that any fraction would be undefined wherever the denominator is equal to 0. So if we were to set these down here and say, what's the zeros? What are the zeros of the denominator? We'd say, well, solving each of these factors, we get positive 2 and negative 1. So we have two vertical asymptotes. We say one at positive 2 and one at negative 1. So for the first time in my videos, at least, we're looking at a graph here that has two vertical asymptotes. So we'd say one at x equals 2, and we say one at x equals negative 1. So these are these undefined spots that are, as our x values get really close to them, our y values are either going to increase or decrease, like without bound. Okay, so we say x equals negative 1. And last but not least, we'll talk about a horizontal asymptote. It either has one or it doesn't. And what we do is we compare the degree of the top to the degree of the bottom. I notice that I have a first degree over a second degree, so this is bottom heavy. So this is wonderful. It just means that y equals 0. Or, I've got people from time to time, they just say x-axis, It's going to be the x-axis that is our horizontal asymptote. So we say here, that is right here. So now, just like in my previous videos, all we're going to do is we're just going to plug in some extra x values, but you need to table them. That means make a table, please. So we say x, y. And in terms of what x values you should plug in, the rule of thumb is this. Always sum to the left and right of your x-intercepts. So like I'd plug in, say, 1 here because that's to the right of this x-intercept. But also maybe 2 to the left and 2 to the right of every undefined spot, every asymptote. So for example, I had an undefined spot at x equals negative 1. What this means is then we'll plug in, say, negative 3 and negative 2. And I say, well, I'm not going to plug in negative 1 because that's undefined. I don't need to plug in 0 because we've already done this. Let's plug in an x value of 1. I can't plug in 2 because that's undefined, so we're going to plug in 3 and we're going to plug in 4. And again, this is why, another reason why we factor the very first expression, not just to simplify it, but because it becomes a lot easier to plug in expressions into factored stuff. So for instance, I say 3 times my input over, let's say, this minus 2 times this plus 1. And we're just going to start shoving in x values. So for instance, if I put in a 1, and a 1, we just get this. We get 3 on top. And in the basement, 1 minus 2 is negative 1. So negative 1 times and then 2. So basically, we get 3 times negative 1, 3 divided by negative 1 times 2, which is negative 3 halves. So we're going to go ahead and fill that in there. That's when we plugged in 1 for x. We got negative 3 halves. So we say negative 3 halves. That's on our graph. Okay, so what if I plug in 3? What if I plug in 3? I get 3, 3, 3. This gives us 9 on top. Over 3 minus 2 is 1. and then we say 3 plus 1 is 4. So basically 9 over 4. We're going to leave it that way. I don't mind rational expressions. We say 9 over 4. If you want to grab a calculator, that is 2.25. You can go ahead and check it there, but leave it as a ratio, okay? Next, we say, well, plugging in 4. We say 4, 4, 4. Looks like we get 12 on top. Over 4 minus 2 is 2. 4 plus 1 is 5. So we get 12 tenths. 12 tenths for this expression here, okay? So this will be 12 tenths. This would be the same thing as 1.2. And then going left, we say, well, what if I plugged in a negative 2? We'll get done with these really quickly here. We say negative 6, negative 4 times negative 1. Negative 1. We're going to multiply those. So we get a positive 4 in the basement. So negative 6 over positive 4. Negative 6 over positive 4 is negative 3 over positive 2 when you reduce that. So we get negative 3 halves. And then we'll go ahead and plug in negative 3 here. We say negative 3. What are we going to end up with here? And we get negative 9 on top over negative 5 times negative 2. So we end up with this, negative 9 over 10. So negative 9 tenths. So all we need to do now is basically we're going to go throw these points on our graph and use what we know about the behavior of rational functions to kind of come up with what this graph looks like. So a negative 3 from the origin, we'll go left 3. We're going to go down 9 tenths. That's like 0.9. You know, that's right here. Looks like we have negative 2 is down 1.5, so left 2 down 1.5. That's going to be this point here. We already plugged in 0 and got 0. If we plug in 1, we get negative 1.5. So at 1 here, we're down 1.5. That'd be this point right here. And then I say, okay, also on the right side, 3 comma 9 fourths, which is 3 to the right, and then up 9 fourths, which is, here's 8 fourths, here's 9 fourths. This would be about 2 1/4. And then last but not least, 4 comma 12 tenths, which is over 4, basically one more to the right, and we say that's up 1.2. So that'd be right here. Okay. So now what I can tell you is when we sketch this in, knowing what we know about asymptotes, we know that way out on the left, our y values would be getting really close to that asymptote, that is our horizontal asymptote, and as we get really close to this vertical asymptote, our y values are going to decrease in this case without bound. And the same thing on the right. It looks like I think we could say without a doubt that our right side, sorry about it's hard to sketch from right to left, the right side looks like this, okay? But in the middle, I do want to comment on this. Now, when we solve for x-intercepts, I did get an x-intercept. I got x equals 0 was an x-intercept. This guy right here, that's one of my zeros. And that occurred once. And so in previous, graphing activities, we say this has a multiplicity of 1. And the important thing here is this, multiplicity of 1. It's odd, which means we're actually going to cross the x-axis at this spot. So when I graph this middle part, I don't go down and back up again. And as a matter of fact, we can indeed cross a horizontal asymptote in the middle. That's fine. I mean, I don't have a problem with that. It's out on the ends that it gets really close to this y value of 0. But this would be a good graph to kind of study because this graph actually crosses the horizontal asymptote here in the middle, and that's fine. In the next video, we'll talk about discontinuity in this graph.